Hi everyone. Today I would like to talk about Bayesian networks. So this is the first video in the series of video I have regarding the package that I wrote in Python, tsBNgen. The package is available in my GitHub. I will put a link in the description to this package. So tsBNgen is a package to generate the synthetic time series data according to the arbitrary dynamic Bayesian network structure. I received a lot of email regarding this package. A lot of people actually like the package. Some people had a hard time running it because the documentation I have in the GitHub apparently is not really well written. So I thought that it's better to create this set of videos. If you like this video, please subscribe to the channel and like the video. It helps me actually create more videos because these videos actually are taking time. So this is the first video, and after that, I'm going to actually walk you through the package. The second video is going to be me actually explaining what the package does. And then after that, I'm going to walk you through the package, how to run them, code, and what commands you can use to actually get what you want. So this video is an introductory video. I'm talking about the Bayesian networks. These are the topics I covered here: introduction, Markup property, probability distribution, factorization, Gaussian Bayesian network, and discrete Bayesian network. So this is a prerequisite to understand what that package is actually doing. So let's start. All right. So these are the topics that we're going to talk about. That now let's start with the introduction here. So directed graph. So what is a directed graph? So what is a graph first? Graph is a set of nodes that represent the variables, right? And the edges. These edges, right, can be directed or undirected. So edges, I would say node and the edges. So now we kind of have different type of graphs. These edges show the dependency or relationship between the nodes. Based on whether these edges have a directionality or not, we have a directed graph or undirected graph. So we can have a directed edge, and we can have an undirected edge. All right, great. So now that we know this, if I name these figures as like have A, let me just use a lowercase here, A, and this is B. So the graph A, as you see, the edges do not have any direction. So this is called undirected graph, right? This type of graph, the undirected graph, also are called Markov random field. Markov random field, MRF in short, right? And then the directed graph, they are also called DAG, or the DAG is actually should not have a loop, but these are usually called Bayesian network, Bayesian network, right? So DAG means directed acyclic graph, that which I'm gonna talk about right now. So these depends on whether the edges have a directionality or not. We have different properties for this graph. We have different inference, different way to model this. Now, what I'm going to talk about today is going to be mainly on Bayesian networks. And what I'm going to walk you through in the second and the third version of this video is going to be Bayesian network or causal network. And the tsBNgen package also is going to be based on the directed graph. All right. So what is DAG here now? In a class of the directed graph, we have something called DAG. And that's what Bayesian network is. DAG means directed acyclic graph. So it's a directed graph like a B that you are seeing here, but it has no cycle. So when you start with node A, you won't go back to node A, right? So for example, if I have a A here, and then A go to the B, let me see what I can. And then B go back to A. This is a loop. This is a cycle. We don't have this in DAG. DAG is directed acyclic graph. The DAG also is called Bayesian network. It has nothing to do with the Bayes law, but it's called Bayesian network, right? So these two terminology are the same. All right. Now, there are some differences between Bayesian network and causal network. It doesn't have to be causal, but for now, we are not going to get there. All right, so now let's talk about the undirected graph a little bit. Why do I want to talk about this? So I said the undirected graph, the edges do not have any directionality. another way to look at that is that, you know what, not only they have directionality, but we have a bidirected edges. So this A to B, this one, you can look at that in a graph in the right-hand side. There is an edge from A to B, and there is an edge from B to A. So on directed graph, by default, they have actually cycle. You can also think of it like that, right? So they are bidirected edges that we don't really have any direction, any determined direction actually for the edges. So and on directed graph, another way to think about that is a bidirected edges actually. So if then there is an arrow from B to D, or when there is an edge between B and D, this means that there is an arrow between from B to D, and there is an arrow from D to B, which I show you like this. All right. Great. A lot of algorithms actually are developed, inference algorithms are developed on the undirected graph. So sometimes actually what you do is you get a Bayesian network or directed acyclic graph, and you moralize that. You remove the directionality and you kind of marry the parents that they have as a common child. We're not going to talk about moralization actually here, right? But a lot of ideas are developed on undirected graph, and that's where the undirected graph becomes really attractive in the literature. Now, let's talk about the directed graph here. There are a couple of concepts that are very vital in directed graph. One here is that parent and child relationship. What is the parent? If you have a node here, like take node A, when you have an edge from node A to some other nodes, the A is called the parents of these nodes. So for example, A, the child of A is B and C, right? Because there is an edge from A to B, and there is an edge from A to C. Now the child of B is only D. The child of B is only D. Child means that it has a parent, or there is actually arrow coming to it, right? Now what's the child of C? Is D as well, right? Great. And what's the child of D? Empty set. D has no child. Very important, right? But now that D has no child, another important thing to look at that is that what's the parent of A? What's the parent of A? A has no parent. So these are worth talking about that. A has no parents, and D has no children. All right. So it takes us to some important concepts here. The root node and the leaf node. They are very important concepts. There is some actually argument on how to define the root node in a graph. But at least as far as I know about that, and the right definition for the root node is a node that doesn't have any parents. A root node is a node that has no parents. So A here is a root node. I wrote that here actually, A is a root node. And a leaf node is a node that doesn't have any children. So no parents, no children. You see, these definitions are exactly the same. So this is a graph. When you take your machine learning courses and you're introduced to the concept of ensemble method, decision tree, right? You are actually, you realize that what you do, you keep splitting these variables until you get your leaf node. And what's a leaf node? Is a node that has no children. And you start from the new root node. And what's a root node? Is a node that has no parents. So these are important things that you should be master of when you're actually going to the directed graph and the Bayesian networks. Okay, great. I talk about that extensively when I actually talk about the package. Great. Now let's talk about the Markup property. We get actually to some interesting stuff for the factorization, but before that, we need to understand the Markup property. So in a like a non-technical term, what's a Markup property? It says that condition on the present, the future, and past are independent of each other. What does it mean? It means that let's say you want to forecast the weather, right, for tomorrow. What does, if the forecast is the weather is actually following the Markup property, what it means is that if I tell you the weather for today, you don't really need to know the weather for the yesterday or any other past weather in the history. Like, all you need to know is the weather for today, and then you can forecast the weather for tomorrow. Do we have Markup property in real world? Not really, but this actually allows us to simplify the problem a lot. So the diagram that I have here is known as a hidden Markup model. I've done quite a lot of research on hidden Markup model, and I will share actually my package It was implemented in MATLAB, R, and Python actually, and in my GitHub actually. But then for now, hidden Markov model is a type of directed graph. You see the directionality? Usually in hidden Markov model, this H is called the state. They are hidden, and this O is the observation, and that's why they are different color, right? So if we want to analyze that, the H1 here is a root node, for example, has no parents. The O1 is a leaf. So all the observation in this H1, they are leaf nodes actually, right? And then this is very related to what we do because it's a dynamic Bayesian structure. So hidden Markov model, or in a short HMM, is the simplest, one of the simplest dynamic Bayesian network structure. Bayesian network, tsBN in short. Let's take a look at what this equation 1 says. It says probability of h of t, something here. Condition on all the past states, h of t minus 1, h of t minus 2, all the way to h1, all this, right, is equal to probability of h of t, condition on the most recent one. That's what Markov assumption is, right? So this is the, let's say, future. Here, this is the present. So you can take this one, h of t plus 1, h of t, for example. So here, for example, this is a future, this is the present, and this is going to be the future and present. All the past states, we don't really care about that. So this is a Markov assumption. It helps us a lot when we want to factorize a graph, right? So why do we use a graph? Perhaps I have to give you this intuition first, is that this actually makes the modeling inference very easy. The d-separation concept actually become very easy using graph. And of course, the causal inference become very easy as well. My research actually was in the intersection of machine learning and causal inference. So that's why I'm really interested about the graphical modeling. Let's continue. So we talk about the hidden Markov model and this Markup property. We are not concerned about the hidden states for now. We want to only understand the Markup property. Another thing is a Markup property to understand is a Markov chain. This is another example here. So Markov chain and hidden Markov model are very similar actually. This is a doubly stochastic process, hidden Markov model. It's like the states follow the Markov property. So now here we don't really have any hidden states for a Markov chain. And let's take a look at what we have here if we want to understand the Markov property. So the second equation here, it says this one. It says P of x4 condition on x3, x2, and x1. According to Markup properties, P of x4 given x3, only to the most recent state. Okay, DAG will show this one very well. Another way for people that have heard of this concept is the d-separation. If you condition on this x3, right? You remember x3, we haven't talked about this. X3 is not collider. So you actually created this separation between x2 and x4. So condition on x3, x4 and x2 and x1 are independent of each other. Now let's take a look at this one. You have x3, x2, x1. This is x3, this is x2, the most recent one. So it's equal to P of x3 given x2. And this one remains the same. Okay, great. So now that we understand this factorization, it's time for us to see how we can actually use it to factorize the probability distribution on a graph. All right, so it's a very famous theorem here, is that the joint distribution of all the variables is nothing but the product of these conditional probabilities, where this xi is a node and this parent of xi, condition on the parent of xi. So if you look at here, for example, here we have x4, x3, x2, x1. See, x2 and x1 are not parent of x4. They don't have any edge to x4. So another way to look at this is that this is going to be x4 condition on x3, because x3 only is parent of x4. It has an edge from x3 to x4. So what all this one says is this, is that the joint distribution can be factorized using this equation. Now, if it's still very abstract, let's take a look at this equation. We want to apply it here. How do we do that? You can start from any node in a graph, no worries. But my suggestion to you is that start from the root node. What is a root node? Is a node that doesn't have any parents. So node A, start from node A, right? you write P of A. You don't even need to look at this equation. P of A times, what is the children of A? We have B and C. Let's go to B. Times P of B given A, parent of B, right? Then what's another children of node A? C. Times P of C. What's the parent of C? A. And times what's the children of B or C? D. Times P of D given B and C. Why? Because B and C are both parents of node D, right? You could start from D, right? But it's just this one shows the way that, for example, when we talk about the forward sampling, this shows the way the sampling actually works on a graph, right? So this is more natural. As long as you know this rule that a node only depends on its parent or condition on the parent of a node is separate from any other nodes, right? So that would be the factorization for this graph, which I have it here for you as well. This is the same thing that I talked about that here. Now, so you start with P of A, P of B given A, and then you could, for example, go to D right after that, and then go back to C. So there are different ways you can think about that. Different way of, this is related to the algorithm classes, perhaps the DFS and BFS, right? But for now, consider that this is a better way of factorizing this graph, and it's less prone to mistake. Great. All right. So I have the factorization for this graph as well here. The Markup property here. Let's take a look at this. Now, what if we have a sequence? So this was a static Bayesian network. This is a static Bayesian network. It doesn't really have any temporal. It means that the network is not repeating itself through time. A static Bayesian network, right? Great. But this one is a dynamic. This is still dynamic. Very simple though. This might be the simplest one. This is even simpler than the Markov one. Dynamic Bayesian network. Markov. This is a Markov chain. All right. So we want to do this joint distribution. What do we do? Again, you don't want to make a mistake. Start from a root node. What's the root node? X1. P of X1. Then go to the child of that. P of X2 given X1. Then to the child of X2. P of X3. Now, okay. So you write all the variables first. First, we are not using the Markup property. What we are doing here is that simply we are using what we do for the probability factorization, like a Bayes theorem. P of X3 given X1, X2. But remember, we said that condition on the parent of a node, the node is independent from any other nodes in a graph. So what's the parent of X3 is X2. So you do know that immediately this becomes P of X3 given X2. So I wrote it down here. This is the factorization using Markup property. And if you write it in a product notation, you get this one, right? And this X1 doesn't have a parent. This is that's why it's actually separate from the other nodes in the conditional representation. But you see that it's actually very hard to make a mistake when you want to be able to write it like that. Start from root node and then keep doing this all the way you get to the end of a chain. All right. Now let's talk about the Gaussian Bayesian network. You don't find much information on the internet about Gaussian Bayesian network. At least you don't find much easy to understand information about Gaussian Bayesian network. What does Gaussian Bayesian network mean? What is that? It's a network that all the nodes are continuous and they follow Gaussian distribution, normal distribution. All right. So now, by now, we have a good understanding of the Bayesian network. See that we have a directed graph. Y is continuous, X1, X2, and X3 are continuous because they're Gaussian. So what does it mean? It means that the X1, see X1, X2, X3, none of them have a node. None of them have a parent, sorry. So they are root. They are root nodes. All right, good. So since they don't have any parent, their distribution or their marginal distribution, and we know they are Gaussian because the Gaussian Bayesian network, and the Gaussian distribution is represented by a mean and only a variance. So here, assume the dimensionality is 1. If it's not 1, mean vector and covariance matrix. All right. Great. So this is what we have for X1, X2, X3. So this is up to now is easy. But what is Y? Y has three params, x1, x2, x3. How do we represent this one? Right? How do we represent that? The way we represent this, we say that the mean of Y, expected value of Y, you see, this when you write in normal, this the first, this one is mean, and this is the variance. All right. So mean of Y is written as the linear combination of the params value. So how would you represent that? Y is like a regression. Consider to be like it's like a linear model, linear regression. So expected value of Y is gonna be what? Beta naught is the intercept, beta 1 x1 plus beta 2 x2 plus beta 3 x3. And that's what I wrote here. And that's how we create a dependency. And then the variance of Y is a constant variance. All right. Okay. So that's how we represent the Gaussian Bayesian network. Now, discrete Bayesian network. What is it? This is easier to understand. The nodes follow, they are discrete and they follow multinomial distribution. All right, so look at this network that I have here. Again, directed graph, and now all the parameters are discrete. What do you mean discrete? So for example, A can be binary, can take value of 0 and 1, 1, 2, 3, 4, as long as it's binary, 0 and 1, for example. This means the probability of that A, that's what this table represents. Probability that A is equal to 0 is 0.6. Probability A equal to 1 is 0.4. That's what the discrete representation means. Here B also is binary. It doesn't have to be binary. It's just only for simplicity because I have to represent C as well, and the size actually grows. I will explain about that once we get to C. But B is the same thing. B is binary, right? Or multinomial, for example. Here, for example, it's called the Bernoulli distribution. P of B equal to 0 is 0.7. P of B equal to 1 is 0.3. Tabular representation. All right. Now what about C? What is C? So C has A and B as a parents. We do know that the distribution of C depends on A and B. How would you represent that? You represent it in a discrete domain as a form of tabular. But how many different possibilities we have? You see, C assume is binary. Assume C itself is binary. All its variables are binary. Well, A is binary and B is also binary. For any representation of the A and B, C can be 0 or C can be 1. Therefore, we have 8 different possibilities, right? If you want to better understand this using combinatorial approach, you can say that, write it like this, A, B, C, right? So this C is actually the node itself. These are the parents. Parent 1, parent 2, and this is parent 3. All right. So what I'm trying to say is that the A can take 0, 1, 2 possibilities. This 2 possibilities, and C can take 2 possibilities. So we have 2 to the 3, and we have 8 possibilities in this network. Let's go over this table together. So what it means is that what is the probability that C equal to 0 given A is 0 and B is 0? Okay, so now whatever this value is 0.4. We don't care. Now, so we can say that what's the probability C equal to 0 given A is 0. Okay, so this one should be okay, so is C equal to 1, for example. I have what's the probability C equal to 1, A is 0, B is 0. This one way also to show that it's equal to 0.6, but they have to add up to be 1. All right, so another way to think about that, I'm gonna see what I can do. Can I copy this one? I want to write on this for you. Oh, if not, no worries. Okay, so let's paste. Great. Let me just talk about something here. There is another way to show this one here. Oh, okay, so it's part of the image. No worries. So this one, another way to say that is that A is 0, B is 0, C is 0. Right? You get probability 0.4. This is ABC. Another way to say that is that, okay, C is 0 again. What if A is 0, B is 1? Right? So for example, the value of this one, you can Look at the from this graph is 0.5. What if now I tell you A is 1, B is 0, C is 0? This way, I want to show you another approach. So this one is 0.7. And what if A is 1, B is 1, and C is 0? This gives you better intuition. This is 0.9 on this graph. All right. So what I'm trying to tell you is that for any value that C can get, you have to consider different possibility of the parents. This is give you better intuition. So if C had 3 possibility, you could say that for C equal to 0, A and B can have 4 possibility. C equal to 1, 4 possibility. C equal to 2, 4 possibility. So we have 12 different possibilities. Or you can use this approach, the same thing. But this one will give you very good intuition actually on how to actually make a reasoning about number of possibilities and how you can represent the discrete graph. All right. In the tsBNgen, I use a combination of the discrete and continuous, and I walk you through that, how I actually model this distribution and how the package exactly works. So if you like this video, please subscribe to the channel, like the video, share it with your friend. And the package tsBNgen is available on my GitHub. And hopefully I see you in the next video. Thank you so much.